Good day, grade 11s. Welcome to your next lesson on Newton's law of universal gravitation. In the last lesson, we watched a little video which basically gave us a feel for Newton's law of universal gravitation. But in this lesson, we're actually going to look at it a little bit more carefully. So first of all, let's look at the definition. The definition says that each body in the universe, so everybody in the universe, attracts every other body. Okay, attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now that was actually covered in the last video. In other words, there is a force between any two objects, whether it's between the pen on your desk and the ruler, or between the book and the laptop that you might be watching this on, or your cell phone and the gum wrapper that's next to the cell phone. There are forces of attraction between all these objects, okay? And they are directly proportional to the product of their masses. In other words, we've got to multiply the masses, and inversely proportional to the square of the distances. The further they're apart, the weaker the force. And in the last video, you also saw that they worked out through lots of experimentation that this big factor G here, which is called the universal gravitational constant. So this is the universal gravitational constant, and this actually makes it true. Before, everything was just proportional, but now the force is actually equal to G m1 m2 over r squared. And in the last video as well, they told you that it was 6.67 times by 10 to the minus 11 newtons meters squared per kilograms negative 2. You do not need to memorize this. It is on your formula list. It's on your formula sheet, and you'll notice that it is only 6.7. So at the moment, all you need to be using is 6.7. Don't go around using 6.67 even if you remember it. Use whatever's on your formula sheet, your data sheet, because that's what they're going to be marking you on in the final exams. So always make sure that you use what they're given. Okay, so that is Newton's law of universal gravitation, and we are going to do more examples using this, but let's talk a little bit more about other things at the moment. First of all, we need to know the difference between weight and mass, because that is very important. Now, mass is the measure of the amount of matter that we are made up of, and is measured in kilograms. So if I go off and I fly off to the moon, my mass doesn't change, okay? Your mass doesn't change. Unless you lopped off an arm or did something extreme, your mass doesn't change. But your weight is the force with which you are attracted to the surface of the Earth or any planet, and it's measured in newtons. So your weight is the force, and that changes. So if you look here, we've got a little graph. And this is the gravity on the planets, okay? And you've got, it's comparative to Earth. So if Earth's gravity was 1, then you would see that Mercury is much smaller, whereas Jupiter is 2.5 times as big. And you will see that we've got Mercury, Venus, Earth is 1, and then Mars is much smaller as well. So what does this mean? This means that on Mars and Mercury and even Pluto, even though Pluto isn't really a planet anymore, okay, the weight is much smaller. So we will be able to jump way higher, right? Whereas on Jupiter, our weight would be 2.5 times, the force with which we're being attracted to the planet is 2.5 times what we're attracted to the Earth. So we would barely be able to lift up our legs. In fact, I don't even think we'll be able to stand up under this force of gravity. So do you understand that the weight is the force with which you are attracted to the Earth or the planet, whereas the mass is the amount of matter that we're made up of. Okay, and that's that's a big difference. Now, free fall. This is when something falls, and the only force acting on it is the force of gravity. Okay, so free fall is when something falls, and the only force acting on it is the force of gravity. Weightlessness, which is what this picture is about, okay, basically the sensation that we experience when our weight appears to be zero. and astronauts experience this in space. And what they're doing here is there are two ways to do this. They've either got a special machine at NASA, or possibly this is in an aeroplane. And what they do, they fly the aeroplane up into the sky, and then they go quickly down, and for a very brief moment you feel weightlessness, because the force up and the force down are equal, therefore there's a no net force on you. And you can see, look, the hair's flying everywhere, and you can see they're having fun and they're all flying all around, and that's because they're experiencing weightlessness. It feels as if their weight is zero. Okay? Gravitational acceleration. Now that is the acceleration of an object in Earth's gravitational field. Now at the moment, I'm talking about Earth's gravitational field, but if we were living on Mars, then this gravitational acceleration, little g, would be what we were feeling if we were living on Mars. So it's specific to the planet. And most importantly, this acceleration is independent of the mass of the object. Independent of the mass of the object. So let me prove this to you mathematically. We have Newton's law of universal gravitation, which gives us that F is equal to g m1 m2 over r squared. So let's pretend that we've got a little man, and he's standing on Earth. Okay, he's a big man. And his mass is m1, and the mass of the Earth is m2. Okay, and he is a distance r from the center of the Earth. So the weight that he feels is g m1 m2 over r squared. But we also know, according to Newton's second law, that the weight that he feels is his mass times little g, right? So these forces are the same. They can't be different. That's the same weight that he's feeling, right? Therefore, we can say m1g equals big G m1 m2 r squared. But look, these masses are the same. He hasn't chopped off a leg or an arm, so that is the same. So therefore, we get little g is equal to big G m2 over r squared. Little g is equal to big G m2 over r squared. So in other words, the acceleration that we feel as we're falling to the surface of the Earth, if we jump out of an airplane, is dependent on the mass of the Earth, or the mass of the planet, and how far we are from the center of that planet. Okay, and now there's a little video that I want you to watch. It's very cool. It's on bowling ball and feathers that are actually dropped. It was actually dropped in a vacuum. So just watch this. It's very cool. Okay, wait.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
Right, grade 11s, I hope that that experiment basically showed you exactly what I was trying to say, that the acceleration due to gravity is totally independent of the mass, and that in a vacuum, even feathers and a bowling ball that have different masses will fall at exactly the same rate. The reason the feathers fall slowly in real life is because the friction caused by the feathery material and their cross-sectional area. Right, grade 11s, hope you have a great day.